Okay. Thanks very much, Lash, for your kind introduction. And good afternoon, everybody. It's a great honor for me to be here. So today I'd like to introduce you nano-cellulose vehicle, NCV, which we made using cellulose nanofibers material and demonstrated at Tokyo Motor Show in October 2019. So let me explain a story behind the NCV project. At first, I'd like to start to explain my research background. I enrolled master course of Wood Research Institute of Kyoto University in 1982. I learned a relationship between the structure and the physical property of wood. For example, the relationship between microfiber angle and the Young's modulus of cell wall. For my PhD, I studied the improvement of the acoustical properties of wood for musical instruments. I made a violin and biochemical treatment, and I received a PhD from Kyoto University. After the PhD course, I continued the study of acoustical properties of wood for another 5 years. Then I changed my research topic to the production of high-strength wood because I found that the tennis racket structure is very similar to the structure of wood fibers. Also, I met very interesting paper published in 1983. In the paper, Dr. Page demonstrated that the tensile strength of pulp, kraft pulp, reaches 1.7 gigapascal. That is 1700 megapascal. The tensile strength of pulp indicated that the tensile strength of cellulose nanofiber, cellulose microfiber, reaches around 2.5 gigapascal or more. As the strength of steel using for automotive door and the bonnet is around 300 to 400 megapascal. Cellulose nanofiber is more than 7 times stronger than steel, while the density is 1/5 of steel. The high strength of cellulose nanofiber is attributable to its semi-crystalline extended molecule chain structures. Because of these structures, CNF has high strength comparable to that of the aramid fibers, as well as high rigidity. So at first, I made 100% cellulose nanofiber material using microfibrillated cellulose donated from Dicel Chemical. Squeeze out water by pressing using porous metal. After that, oven dry the cake and hot pressed at 150 degrees, 100 megapascal for 30 minutes. This is a stress strain curve of 100% MXC. The strength reached 250 megapascal in bending because of the hydrogen bonding between CNF's network. And when we add oxidized starch just to 8%, the strength reaches 300 megapascal. I was so excited with these results. Then I further tried to make much more high-strength material using MFC or CNF. When we prepared CNF sheet and impregnate the PF resin and hot press them after lamination, the strength of the material reached 400 megapascal This is as strong as steel using for automotive, while the density of 1.35 gram cubic meters. And in 2003, we developed an optically transparent and low thermal expansion cellulose nanofiber composite. The composite is as strong as steel, as thermally stable as glass, and as flexible as plastics. This is a preparation process of optically transparent composite. At first, we prepared CNF sheet by vacuum filtration of CNF aqueous solution, then impregnated acrylic monomer to get rid of air inside. Also, we developed cellulose nanofiber reinforced natural rubbers in 2006 using unmodified CNF, and in 2011 using hydrophobic esterified CNFs. 3% chemically modified CNF increased rigidity of natural rubber by 8 times. 5% of chemically modified CNF decreases thermal expansion of natural rubber from 226 ppm to 18 ppm. That is almost steel. Since then, I had been dreaming to make an automotive from forest using high-strength CNF material and optically transparent low thermal expansion CNF materials. To make my dream more realistic, we developed melt compounding process to make CNF reinforced plastics, because among many expecting application of CNFs, there is a great demand for the reinforcement of thermoplastic resin. If we replace 10% of plastic by 5% of plastics by $8 per kilogram CNF, it generated 120 billion market. Then we studied the reinforcement of thermoplastic by CNF using melt compounding. This is a production system which consists of esterification of CNF, melt compounding, chemically modified CNF with PP and PE, injection molding of the compound to make nanocomposite sample for the test. We study the effect of functional group incorporated on the surface of CNF for the reinforcement of PP and PE polyethylene using linear fatty acid and cyclic fatty acid. This is a part of the results of mechanical properties for PP and adding CNF 10 weight %. We clarify the relationship between reinforcing efficiency and the chemical structure incorporated and the dispersibility of CNFs at DS of 0.4. This is a result for polypropylene, and this is a result for high density polyethylene. You can see that the longer chain improves dispersibility of CNF in polyethylene and increases mechanical reinforcing efficiency. However, it was found that incorporation of rigid structure gave higher reinforcing efficiency than long alkyl chain. On the basis of these results, we focused on ASA treatment. ASA is alkenyl succinic anhydride, and this is a structure. It shows that the 10 weight % CNF addition increases rigidity of high-density polyethylene by 4.5 times and decreases the thermal expansion to 1/5. However, there was a big hurdle to commercialize ASA-treated CNF reinforced PP and polyethylene. That is a production cost. Pulp is around 50 cents or $1 per kilogram. But after this integration of pulp to make nanofibers, the price increases $20 to $50 per kilogram. Then we studied a process to reduce production cost and found that when we ASA treat the surface of every single cellulose nanofiber in pulp, it was found that the treatment allowed this integration of dried pulp and well dispersion of CNF in polymers during melt compounding. Here, you can see that dried pulp nanofibrillated during melt compounding. So before supply to the extruder, put in the extruder, it is pulp. But after melt compound, it becomes individualized cellulose nanofiber that reinforced polymers. We name this integrated production process as Kyoto process. That is a process simultaneously nanofibrillate the dry pulp and uniformly disperse the CNF in the resin. For the Kyoto process, in addition to ASA treatment, we are using acetylation for polyamide 6 or PLA because acetylation improves the thermal durability of CNF by around 20 degrees, which allowed melt compounding with polyamide 6, which has a melting temperature of 225 degrees. 10 weight percent CNF reinforcement using acetylated pulp and the Kyoto process increases Young's modulus of polyamide 6 from 2.22 gigapascal to 5.3 gigapascal, 2.5 times. Acetylated CNF disintegrate by Kyoto process also increases rigidity and strength of PON, polyacetal, PLA, PBT, around 2 times. When we mix 10 weight percent acetylated pulp with polypropylene, compatibilizer, and inorganic pillar, then kneaded it at 200 degrees Celsius, the Young's modulus of PP reached 2.5 times of the neat resin. The strength became twice. Forming is an important part of cellulose nanofiber composite to make lightweight automotive parts. Supercritical carbon dioxide or nitrogen forming is applied for this case. Here, you can see that cellulose nanofiber contribute to make tiny bubble than inorganic pillars. At the same time, it gave quite smooth surface of the formed product. These are engine covers of automotive produced by injection molding at 280 degrees Celsius. Cellulose nanofiber reinforced formed polyamide 6 reduces the weight of engine cover by 30% compared to glass fiber reinforced polyamide 6, while keeping same rigidities. because of the foaming increases the thickness around 1.5 times. Material recycling ability of CNF reinforced plastics should be noted. Because of the nanofiber reinforcement, CNF reinforced plastic is material recycling. So crush and injection molding, and crush again, injection molding, and crush again, injection molding. We repeated material recycling. And the cellulose nanofiber reinforced high density polyethylene keep same tensile modulus and same keep the constant tensile strength. On the other hand, glass fiber reinforced plastics cannot. Seiko PMC constructed commercial plant based on Kyoto process of ASA treated pulp in 2017. And the Nippon paper constructed a test plant based on Kyoto process of acetylated pulp in 2017. The product from Seiko PMC commercial plants are being used for midsole of ASIC running shoes from 2018, and 7 million shoes were already sold globally. Gathering these technology of CNF material, we started a project to make nanocellulose vehicle in 2016 autumn, supported by Ministry of the Environment in Japan. I invited Dr. Usuki, very famous researcher in the field of nano composite or polymer science, to this project as a project leader. He used to belong to the Toyota Central Research Institute. We invited 22 companies and institutions, including Denso and Toyota Boshok, Toyota Motor East, and Asian. Please watch this video. This is the first day that we moved NCB to my institute. So NCB is now moving here. Then this time, I remember that I followed the NCB like a kid, very excited with this. So it's me. Now we are exhibiting this NCB at my institute. So then please watch this video.
和桜と名付けられた淡い桜のボディカラーに和や木、未来を思わせるシャープなフォルム。その車の名前は NCV ナノセルロースビークル。植物由来の新素材セルロースナノファイバーを自動車部材に適用する実証プロジェクトの成果として生まれました。プロジェクトは22の機関が参画。2016年度から CNF を活用した自動車部品等の製品開発、さらに各段階の性能評価や CO2 削減効果の検証に取り組みました。
車を作りまして、13個の部品に CNF を入れて、仕上げたんですけれども、 車全体としての重量が、標準的な車よりも16% 軽量化できた車ができました。それによって燃費が当然向上しますので CO2 の削減効果が非常に大きなことが分かりました。それがその NCV プロジェクトの一番大きな成果だと思っております。
バイオエコノミーあるいはサーキュラーエコノミーという新しい経済概念があります。それは地球環境とか生物圏と人間の経済活動をどのように折り合いをつけていくか、そういった新しいものづくりを具体的に示したのがこのナノセルロースビークルだと思っています。2001年ぐらいに高強度の材料ができると、セルロースナノファイバーを使って、で2003年に透明の繊維強化材料にもなるっていうのが分かって、そうすると鉄に変わるようなものができてきたりガラスに変わるようなものができてきたんで、
木材から生まれたこういう自然由来の素材を自動車という日本が非常に強い産業に使っていくというところが環境負荷を考えた上での社会戦略として非常に重要なファクターになってくるんじゃないかなと思ってます。
でイメージとしては裏山から車ができる時代が来るとか、
やっぱりその矢野先生の強い思いがありましたので、22の参画機関が集まって4年間でみんなでその部品を作って車の評価をしたということであります。
それは各社の技術開発力を生かし、かつてない規模で進められました。インテークマニホールド、エアコンケース、インストルメントパネル、メッキ部品、エンジンフード、CNF サブフレーム、シートクッション、パケトレフロントカバー、その一つ一つから CNF の新たな可能性が見えてきました。
車の世界ではその嬉しさっていうんですけど、きちんと作って評価して嬉しさがどこにあるかっていうのをみんなでこう納得して進めていったと。嬉しさの一つはもちろん強度合成が上がるので、その分製品としての薄肉化ができると。だから部品としては非常に軽い部品になる。でそれが車にとっては一番嬉しいところなんです。
13もの CNF 部材を搭載した試作車がいよいよ完成。その主な特徴を見てみましょ
う。軽くて強いというのがセルロースナノファイバーの一番の特徴なんです。100% でセルロースナノファイバーだけでとても強い材料を作っています。それは自動車のボンネットに鋼鉄の部材の代わりとして使いました。一番やはりマーケットに期待されるのはセルロースナノファイバーでプラスチックスを補強していろいろな形状に加工できるようなものにしたい、射出成形であるとかブロー成形であるといったような成形技術がありますが、それについてはドアの外側、それから内側のドアトリム、ブロー成形によってスポイラーを作ったりということにしています。透明なその材料を作ることができる、これはナノの特徴なんですね。サンルーフのところであったりバックウィンドウであったりというところに使われています。新しいものづくりの形として 3D プリンティングというのは非常に今関心を持たれている作り方ですけれども、セルロースナノファイバーを入れた樹脂の粉末を使いますと 3D プリンターに応用することができるんですね。実際にはホイールのフィンの部分、そういった非常に細かな複雑な形状をしているものはこのプロジェクトでは 3D プリンティングによって作っています。
車の部品だとか部材っていうのは、小さいものから大きなものまでいろいろあるんですけれども、小さいものは比較的簡単にできるんですが、大物の部材となるとやっぱりその平面性をきちんと出すだとか、あるいは表面の平滑性ですね、それをきちんと出すことが非常に難しかったという印象です。
NCV プロジェクトの成果には多くの期待が寄せられ、 CNF 素材の持つポテンシャルが実証されました。
やっぱり本当に車ができて走るところまで行ったんだっていうのは皆さん驚きを持って受けてくれてて、やっぱりそこまでの技術力を見せることができているっていうことは良かったですし、
またその自動車のプロの方にもですね、実際にその塗装していない形の部品もその場に展示してあったので、それを見せるとなるほど使ってるねということで理解していただきましたので、訴求効果は非常にあったんじゃないかなと思ってます。 CNF が今後社会実装をされていくためのスタート地点に立った。
次世代の大型産業資材になるっていうためには、これから異分野の人たちが集まってきて折り合いをつけるのは大事なんです。
こっからが勝負だということを思ってますので、これで決して終わりではなくてどんどん進化していきたい。
いいものができたから持ってこいっていう世界じゃなくて、やっぱりその材料が使えるように僕らも苦労するから頑張るから一緒になってやっていこうっていう、そういうオープンイノベーションのスタイルでこの材料はこう育てていかなければいけない。
CNF 素材による脱炭素社会の実現。その未来は私たちのすぐ手の届くところにあるのかもしれません。
And please watch these videos. Okay. NCB has a bonnet made of 100% CNF honeycomb board. And these are injection molded outer parts of the door. Outer parts of gull wing door are made of injection molded foam, 10 weight % cellulose nanofiber, length was PP. And inside door trim is injection molded foam, 5% weight % CNF PP. We made a rear spoiler and front undercovers by blow molding. And seat cushion is made of foam CNF polyethylene. CNF sheet pipe is applied for the frame of NCB. Optically transparent CNF reinforced polycarbonate is applied for the roof and rear windows, back door of NCB. we developed 3D printing technology in this project. Powder bed fusion method, PBF method, was applied for 3D printing fabrication using CNF reinforced polyamide 6 powders. Here you can see 13 types of automotive parts onboarded NCV. In total, we could estimate 16% weight reduction of automotive by cellulose nanofiber materials and the improvement of fuel consumption by 11%. Although we didn't onboard for NCV, we manufactured an air conditioner casing consist of 8 CNF polypropylene composite parts, and the intake manifold consists of 3 CNF polyamide 6 composite parts. We made a big flow parts by resin transfer molding, back door, and instrument panel by injection molding. And these are our recent material. Left side is air conditioning case using CNF reinforced biopolyethylene, and the right side is optically transparent cotton cloth. 10 weight % CNF reinforcement increases the rigidity of biopolyethylene from 1.1 gigapascal to 2.7 gigapascal. And interestingly, it attained 30-degree higher heat distortion temperature, HDT, at 1.8 megapascal than PP talc composite. So HDT of cellulose nanofiber reinforced by polyethylene reaches around 100 degrees Celsius. We also developed cotton cloth. I would say this is a world first real emperor's new cloth. I like these images. So I would like to move to today's conclusion. The 20th century was a century driven by fossil fuel resources. It became clear that we are approaching the limit in the form of global warming and climatic changes. Regarding how we are to live in the 21st century, we cannot expect humankind to become suddenly wiser. At the same time, the level of social demand will grow continually. To fill this gap, we need to show our respect for the mechanism that natural life forms, structures created over hundreds of millions of years and gain their help. At the first day of Tokyo Motor Show, the Minister of Ministry of the Environment, Mr. Shinjiro Koizumi, brought Mr. Akio Toyoda, President of Toyota, to the NCB booth and explained the potential of cellulose nanofiber materials. It was really great honor for us. Those are findings supported our project more than 15 years, endless supporting from the government. So thank you very much for your kind attention. I think that's all.